talk about critical points, local maximum, and local minima. Okay, so what critical points are, if you remember back to grade 10 when we studied parabolas, they are either the maximum or minimum function value that might occur at a point c comma f at c. So maybe on a parabola that opens up, it's going to be minimum, and then on a parabola that opens down, we're going to have a maximum, right? So the calculus aspect of it comes into play where we take a look at, so that turnaround point, the derivative of the function is either going to be equal to 0, or that derivative is going to be undefined. Okay, and critical numbers is C, where C comma F at C is the critical point. Okay, we're also going to take a look now at first derivatives test. So what is a first derivative? When we look at the first derivative, we sometimes call it velocity. And what we're doing is we're taking a look at like tangents to the curve, right? So we're seeing like how fast the curve is moving. So this first derivative test is used to test for local minimum and local maximum points. So let the derivative of f at c equal 0. This is used to determine whether a function is increasing or decreasing on either side of that critical point. Okay, so if we have a parabola like this, we have a local minimum. If the first derivative is less than 0, as you can see here, then we're going to be decreasing. If the first derivative, so the velocity, is greater than 0, we're going to be increasing. Okay, and remember, decreasing and increasing, we can tell because velocity is not only the speed, so like the absolute value of the speed, but also direction, right? So this is speed plus direction, or magnitude plus direction. Okay, and if we have a local maximum, when we have a local maximum when the derivative is greater than 0, maybe it's on the left, and then the derivative is less than 0 on the right. Okay, because it changes from going up or increasing to decreasing, or in the other one, decreasing to increasing. Okay, let's also read this together. So just to summarize what we did on the previous page, when moving left to right through x values, and remember, we always read a graph moving left to right, okay? If the derivative changes from negative, which is of course going down, to positive, we're going to have a local minimum at that point. And if the derivative changes from positive to negative at x equals c, then we're going to have a local maximum at that point, of course, up and then down. Okay, and anywhere that the derivative of f at c equals 0, it may imply something other than a minimum or maximum at x equals c, okay, such as the derivative does not exist, or at this point there might be like a cusp or a corner. Okay, so just note, critical points occur when the first derivative equals 0, and this gives us locations of horizontal tangents on the graph of the function. Okay, critical points that occur when the graph is undefined give us locations of either vertical tangents or cusps. Okay, so again, if it's a turnaround point, there's going to be a horizontal tangent. Okay, and maybe if we have a function that goes like this, okay, there's either going to be a vertical tangent, or perhaps there's going to be a cusp at that point. Okay, local maximum and minimum values are also called local extrema. Okay, local max and mins. Every local max and min value of a function occurs at a critical point of that function. Okay, a local maximum or minimum does not have to be an absolute max or min. It's basically just any max or min on that area of the graph. Okay, so over the course of chapter 4, what we're going to do is we are going to find like a very long, I believe it's 9-step algorithm of sketching graphs. Here's the algorithm so far. So here's just an algorithm for finding the local maximum or minimum values of a function. Okay, so first find critical values. So find the derivative, set it equal to 0, or find when the derivative is undefined. Okay, and then use the first derivative to analyze whether f is increasing or decreasing on either side of that critical number. And then what we're going to do is we're going to, based on the findings in step 2, we're going to conclude whether each critical number locates a local maximum or a local minimum, or neither. Okay, so here we go. Example 1. For the function x to the 4 minus 8x cubed plus 18x squared, determine all the critical numbers. And then what we're going to do is determine whether each of these numbers gives a local max, a local min, or neither. Okay, so the first step here, number 1, is find the derivative. So let's call this y prime equals, we have 4x cubed minus 24x squared plus 36x. Okay, and let's find when that equals 0. So let's just set it equal to 0. We have 4x cubed minus 24x squared plus 36x. I'm going to factor out a 4x, and we're left with x squared minus 6x plus 18. Sorry, that's plus 9. Mistake. Okay, and if we were to factor the brackets, we get x minus 3 and then x minus 3, so it's just x minus 3 squared. Okay, let's solve for when x equals, when this function equals 0. So we get x equals 0, and we also have x equals 3. Okay, so far what we know is that we have a function, and at 0, there's either going to be a max, a min, or maybe nothing. Okay, and then also at 3. Okay, so there's our interval right there. Okay, so what we're going to do is we're going to take a look at this equation from these 3 chunks of the graph. So from negative infinity to 0, so when x is less than 0, okay, we're going to take a look at the graph when x is between 0 and 3. And then we're going to take a look at the graph when x is greater than 3. Okay, so let's just make a chart. Okay, all we have to do, we don't actually have to sub in like real numbers, but all we have to do is analyze each of these right here, each of these factors. So in other words, when x is less than 0, when we sub that in any of those numbers into 4x, does it give us a positive number or a negative number? Okay, so let's analyze everything at 4x. When we sub in a negative number there, we get a negative. When we sub in a positive number, we get a positive. When we sub in a positive number, we get a positive. Okay, that's easy. Now let's go x minus 3 squared. Well, without even subbing these numbers and subtracting 3, anything squared is going to give us positive. Okay, therefore, this graph so the entire graph, a negative and a positive will be a negative, positive, 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 positive. Okay, in other words, if we're taking a look at the derivative of this function, we know that the derivative is negative, therefore it's decreasing. We know the derivative is positive, so it's increasing, and positive is increasing. Because this was less than 0, this was greater than 0, and this one was greater than 0. So if the derivative is decreasing, we know that the shape of the graph is going to go like this, increasing and increasing. So now all we have to do is come over to this graph, and we know that it's going to go down to 0, and then it's going to go back up to 3, level off so that the derivative is 0, and then up again. And completely algebraically, when we go down and then up, we know that there's a local minimum at x equals 0. But there's no local maximum because we have an up and an up, which does not give us a local maximum, only when it's up and then down.